Hey everybody. So obviously I'm not there today. And yeah, let's just get right into it and jump into section 5.2. So if you wouldn't mind getting out your homework, make sure you submit it if you have not already done so. But yeah, let's go through the homework, shall we? Okay, so I've got the key, so just pause where you need to. Okay, make sure you're correcting any work that you need to. Yeah. Just gonna scroll through. Pause where you need to. Just check your work. Okay, and then there's 43. So if you have any questions, if you need to, you can shoot me an email, you can shoot me a remind, and I can kind of clarify any of these problems here. Hopefully, maybe you can talk with the people around you. If anybody's struggling, maybe we can help each other out. Or if you need to, you can go and ask Mrs. Nappolt. She'd be more than willing to help you out with any homework problems. I think you'd be all right. Okay, so let's get guided notes. If you have not already gotten them from the sub, make sure you get those. This is section 5.2, properties of quadratic functions in standard form. So one thing that we talked about yesterday was quadratic functions that were in vertex form, but now we're going to talk about them today in what's called standard form, and we'll find the relationships between them. Okay, so first thing we have to talk about is this thing called the axis of symmetry. I talked a little bit yesterday about how when we're doing the reflections across the y-axis, if the y-axis is the axis of symmetry, then the reflection across the y-axis doesn't really do anything. But what if we shift that away from the y-axis? Well, then it's different. Then the reflection would do something to it. So when I talk about the axis of symmetry, basically it's the line of symmetry of any parabola. Every single parabola has an axis of symmetry. Every single one of them. You just got to find it. Now, the axis of symmetry is a vertical line through the vertex, and that's a really important thing that we have to know. It goes through the vertex of the function, okay? Through the vertex. It always runs through the vertex because that's that centering point. The quadratic function a times x minus h squared plus k has the vertex, has the axis of symmetry. Well, if it runs through h, x must then therefore be h, right? Because remember, any x equals is a vertical line. So therefore, if it's a vertical line, x equals a number, it's going to be x equals this vertex coordinate, okay? So pretty easy example here. Identify the axis of symmetry. Well, then it's just, since the h is -3, right? That would mean that the axis of symmetry, and we will abbreviate axis of symmetry as AOS. The AOS is actually x is equal to -3. If I plotted this into my calculator here, I could see it as well. Let me go ahead and show you. Let's go into my y equals and plug in parenthesis x minus 3 squared plus 1. My graph. So there's my parabola. Do we see here? The y-intercept is at positive. Oh my gosh. Good thing I graphed this. Whoops. Yeah. The h is actually +3. You guys are probably sitting there as this is going to be like, Mr. Albert, isn't it +3? Mr. Albert, isn't that positive? But yeah, good thing I graphed it here, because this would actually end up being at +3. Because you might be able to say, wow, that's a really straight line. You might be able to say that moves it to the right 3 units, right? So that means it's going to push the axis of symmetry away from the y-axis to the right 3 units as well. Ooh, yikes. Hope that's not a precursor to what's come. Okay, so how does how does taking vertex form relate to this thing called standard form? We've discussed sometimes standard form of a linear. Standard form of a linear was that ax plus by equals c, right? But to talk about standard form of a quadratic, I still have a, b, and c, but in this case, it's y equals ax squared plus bx plus c, where I go in descending order in terms of the x squared, the x, and then the x is no longer there. Now, how does that relate from the vertex form to standard form? Well, to kind of show you how it relates, because obviously these have meaning, right? remember that the A, this is the movement, this is a vertical stretch or compression as well as any reflection across the x-axis. This is the movement left or right, and this is the movement up or down. So obviously those things have meaning. So how did those things relate to A, B, and C? That's what we're going to look at here. So I'm just going to start manipulating it. I'm just going to start first by foiling that, right? And I have to, right? Because this is technically x minus h times x minus h plus k, right? So I do have to FOIL this out. So that means that it's a times, okay, first x times x is x squared, outer, minus xh, inner, minus xh, last. Negative h times negative h is a positive h squared, and then plus k. Okay, let's keep manipulating here. We've got a times x squared plus, these are 2xh, it's, and I shouldn't say plus, it's a minus, minus 2xh plus h squared plus k. That's a k, if you couldn't notice. Now I distribute in the a, ax squared minus 2axh plus h squared plus k. And I'm just going to do a little manipulating here. I'm going to say ax squared minus 2ahx plus h squared plus k. All right, so let's take a look here. It was ax squared plus bx plus c. Do we see how these things are relating now? A ends up being a, negative 2ah is b, and this whole h squared plus k ends up being c. Ooh, that's kind of funky, right? Okay, so these things are relating to one another here, right? Oh, did I forget the AH? Man, I'm totally screwing up here, people. I'm so sorry. I didn't distribute to this. I'm really sorry. AH squared plus K is equal to C. So sorry. Ugh, yikes. But, you know, how do these things relate? Well, A is A, no matter what. A in vertex form is the same meaning as A in standard form. A in standard form, that number leading our polynomial, our quadratic, that means the same thing. It indicates whether there's a reflection across the x-axis and or any vertical stretch or compression that's been happening. The fact that B is negative 2ah. Now remember that, you know, we had said that the axis of symmetry was x equals h, right? Okay, well, if I know that h, you know, if I know h is our axis of symmetry, that value, right? I know that b is equivalent to negative 2ah. If I can somehow put this in terms of h, I can kind of set it equal to it. Like here, if I divide this over to the other side, right? I would have b over negative 2a is equal to h. Okay, so that means that the axis of symmetry is x equals no longer h, but negative b over 2a. Negative b over 2a. And that's going to be our formula for our axis of symmetry that we will use when it's in standard form. Lastly, c is ah squared plus k. Now, here's what's cool about this. If I have a times x minus h squared plus k, and I plugged in 0, what would I get in the end? Well, this would be a times negative h squared plus k. Negative h squared would turn into just positive h squared. So a times h squared plus k. Okay. So you're telling me if I plug in 0, I get ah squared plus k. That means that this is a coordinate for every ah squared. This is a coordinate for every single parabola. Yeah. 0, comma, c, because those things are equivalent here, right? So that means that c is actually my y-intercept. Okay, so c is actually my y-intercept. So let's wrap it all up. Let's put it all together. We know all of these things to be true. Now, if a is positive, if a is greater than or equal to 0, and now we're talking about a, b, and c when it's in standard form. Okay, if a is greater than 0, that means there's no negative sitting out front. It has not been reflected across the x-axis. Therefore, if a is greater than 0, it opens upward. If a is less than 0, a reflection has been applied. It would open downward. The axis of symmetry is negative b over 2a. And what is that? That means this is b and this is a, so it's negative b over 2a. Now, the vertex, well, if the x value of the vertex matches the x value of the axis of symmetry, that's negative b over 2a. How do I figure out what the y value, what the up and down value is? Well, just plug it in. Like if this is 3 or something, you find f of 3. That's the notation here. You find negative b over 2a and then plug it in, f of negative b over 2a. And then the y-intercept is always c, or 0 comma c if you wanted to write it that way. The book likes to get funny, and they like to say, when a is positive, the parabola is happy because it's positive. When a is negative, the parabola is sad. Well, opens downward. All right, so let's put that all together and graph this function. So we're going to take this piece by piece. We're going to say, okay, determine whether the graph opens upward or downward, find the axis symmetry, and then find the vertex, find the y-intercept, graph the function. Okay, let's do that. Determine whether the graph opens upward or downward. Well, since a is 2, meaning it's positive, then this graph opens up. Right? It generally has this shape to it. Okay, find the axis of symmetry. Well, the axis of symmetry equation, whoa, tripping out there, is x equals negative b over 2a. Okay, so let's just identify what my a and my b are. Well, my a is 2 and my b is negative 4. A is 2 and b is negative 4. So it's negative 4 over 2 times 2. Okay, so that's negative. This would be negative 4 over 4. So negative 1 turns into positive 1. That means x equals, and again, I'd like you to write it as an x equals because it is a vertical line. X equals 1 is our axis of symmetry. I then find the vertex. Now, how do you find the vertex? Well, you want to plug that x value in. Well, into what? Back into our original. 2x squared minus 4x plus 5. 2x squared minus 4x plus 5. So 1 goes in. 2 times 1 squared minus 4 times 1 plus 5. So 2 minus 4 plus 5 turns into negative 2 plus 5 is 3. 1 comma 3 is my vertex. Now my y-intercept is just my c value. My c value is 5, so my y-intercept is 0 comma 5. Okay. It then says to graph the function, so we're going to kind of put it all together here. If I want to graph this function, I know it opens up. I know the vertex, I think is at 1 comma 3. Yikes, it's jumping around on me. Yep, I saw it there. 1 comma 3. Thanks. 1 comma 3. And then my axis of symmetry was x equals 1, and my y-intercept was 0 comma 5. Now I can use that to graph everything that I need to. Okay, my vertex, 1 comma 3. X equals 1. 0 comma 5. And at this point, all I need to do, if this is the line of reflection, I know I can just reflect this point over to the other side, so that's a 1 over there as well. Whoa. Again, I'm really sorry about my tablet writing skills, but you get the idea. Okay. All right, let's take a look here. Now, substituting any real value of x into the quadratic equation results in any real number. Therefore, this is an important statement here. The domain of any quadratic is a real number, is any real number, all real numbers. The range, well, it depends on, if it's a parabola like this, it depends on where that vertex lies, right? I only want values above this point if it opens upward. If it opens downward like this, obviously, I would want to find out where the vertex is, and I only want y values below that point. So it all depends on how it opens up or it opens downward. Okay, so we can talk about the vertex being a minimum or maximum point when we know whether it opens upward or whether it opens downward. If it opens upward, then it's a minimum value. The domain is always all real numbers, but the range is all greater than or equal to the k value of vertex. The only difference between it opens upward and downward is that if this is a maximum value, it's going to be less than or equal to that k value. Okay. No matter what, domain is all real numbers. The range is dependent upon where the vertex lies. Okay. All right, so let's find it here. Find the maximum or minimum, then define the domain and range. Okay, so the function is x squared minus 6x plus 3. I want to find the maximum or minimum value. Remember, max or min is noted by the actual vertex. So let's plug it in. We know it's x equals negative b over 2a. We've got to find the axis of symmetry first, which means a is 1, b is 6. So therefore it's negative 6. Negative 6 over 2 times 1. So it's going to be negative 3 or positive 3. Okay. I'm okay if you just jump straight to positive 3. So we know, therefore, it's going to be 3 comma something. Let's plug it in and see what it turns out to be. 3 squared minus 6 times 3 plus 3. This is 9 minus 18 plus 3. Negative 9 plus 3 is negative 6. Okay. Now, that's my vertex. Is it a maximum or is it a minimum? Well, it depends on whether it opens it upward or downward. Since A is positive here, it's going to open upward. Okay. So now that means that this is a minimum point. Okay. And now identifying the domain and range. Well, domain is always all real numbers. The range is dependent upon the y value of the vertex, so therefore it's going to be y is greater than or equal to negative 6. Think about it. I only want values above negative 6. So here's the minimum value, and there's the domain. Oops, sorry, cut off my range a little bit there. Okay. Now, I can do that in my calculator. Right? If I wanted to, I could do that in my calculator. Let me show you how. I'm going to show you how with this one. Do we understand that since this opens downward, we know it's going to be a maximum point, right? We know it's going to be some sort of maximum point. Let me show you here what I mean. I can go to my calculator and I can plug this in. Let's clear out that that's there. Negative 3x squared plus 2x minus 4. I'm going to graph it. Now, I want to calculate that maximum point, right? I see that it opens downward. I want to figure out what that maximum point really is, right? So we can say this is going to max at, and then give us the coordinate of the vertex. The cool thing is your calculator will do that for you. If I calculate it, look, maximum value. You just have to kind of work with your calculator. Now look at what it's asking here. It's asking for a left bound. I want to move my arrow. Do you see my trace going along? I want to move my arrow until the trace is to the left of the maximum. It asks me for a right bound now. I want to move my trace until it passes that peak, until it's on the right side of my maximum value. And then it's going to ask me to guess. I just hit enter one more time. And there it is. Looks like it's 1/3, comma, negative 3.6, negative 3 2/3. Repeating. Right? So 0.3, comma, negative 3.6. Repeating. Yeah. So there's how to find it within my graphing calculator. Okay, now, a highway mileage M in miles per gallon for a compact car is approximately this equation, where S is the speed in miles per hour. So, thinking about this, this is actually, at some point, the gas mileage will start to decrease based on speed, right? You go too fast, you're burning the engine too high, the speed, the gas mileage will go down, right? You are too slow, and you're not pressing on the gas very much. Your gas mileage is not as much as so there's some peak speed that maximizes your gas mileage. So let's figure out what that gas mileage would be if I wanted to maximize that. Well, to do so, I want to find the maximum point. I want to figure out what that point actually is. Well, that's negative b over 2a. So x equals negative b. X equals negative b over 2 times a. Okay, let's find out what it is. So I've got, let me get out of this, 2.45 divided by, and now obviously I'm making this positive because my two negatives there will cancel out, And I'm going to put this in parentheses, 2 times 0.025. This is my x value, 49. 49. And that's the x, or s in this case. S is 49. So at 49 miles per hour, that's going to get the best gas mileage. Okay. What is that gas mileage? Well, let's plug it in. We got negative 0.025. Cursor. Negative 0.025 times 49 squared plus 2.45 times 49 minus 30. So my gas mileage is 30.025 miles per gallon. So at 49 miles per hour, it's 30.025 mpgs. Okay. All right. All by finding the vertex. Okay. Because that's the maximum value. It's the maximum value, maximum mileage, which will get you the maximum gas mileage. Okay. All right. Hope everybody's having a good day, and I'll see you all soon, hopefully.